Good morning, I'm Mr. Precella, and today I want to do some financial mathematics problems for my Math 1324 class. This is from Homework 8, the examples I'm going to work today. Homework 8 is a big combo section. We have all the different types of financial problems that we've run into mixed in together, and you're going to have to decide which formulas should be applied. That includes the compound amount formula, the future value of an ordinary annuity, future value of an annuity due, and the present value of an ordinary annuity. And I've circled three that I want to do today. The first one, find the monthly house payment necessary to amortize a 9.6% loan of $254,400 over 15 years. If you're looking at amortizing a loan, we know which formula we're going to have to use there. It is the present value of an annuity, the present value of an ordinary annuity, but we only looked at one present value of an annuity formula, so it's the present value of an annuity, and we know that formula is P equals R times, this is the one with the negative exponent, so 1 minus 1 plus I to the negative n all over I, and realize that 1 minus 1 plus I to the negative n is not the same thing as 1 plus I to the negative n minus 1, so you should have gotten the hang of punching in that formula. Let's come to my scratch paper. This is number 1. So then here, let me get my paper positioned there. So it's number 1. And we know the formula we're going to be using. Let's start identifying what we know from the problem. Do we know the value of P? P, the present value, that's the amount of that loan that you're getting. A loan is an account. At the beginning of the account, the outstanding balance is $254,400. These people are going to pay that off, chipping away over 15 years, so that in the future, eventually, the lump sum is down to 0. But the lump sum in that account at the present, starting off, is $254,400. Do we know R? No, we don't know R. Let me move all of this up some. We don't know the value of R. That's the amount of the periodic payment. So what about I? The rate per period. Well, it's 9.6%, so that'd be a 0.096, but we have to split it up over 12 months. They're not paying 9.6% interest every month. They're paying 9.6%. That's an annual rate. Splitting it up by dividing it by 12. That's going to give us what, a 0.008? Yes, a point. That's it. Now, if it didn't terminate nicely, I'd just use the exact value, the fraction. But since it terminates nicely, I'll use the decimal value. And in how many payments are they going to make to pay this loan off? How many months are there in 15 years? 12 times 15. You probably have that one memorized at this point. That's 180 house payments. For a 15-year loan, there are 180 payments. For a 30-year loan, there are 360 payments. Substituting now into the present value formula. I'm recopying the formula all over before I start substituting in. That P value, that's the $254,400, equals, R is what we're looking for, 1 minus 1 plus I. 1 plus 0.008, that's just a 1.008 to the negative negative 180 all over 0.008, our I value. And to evaluate this, I don't do anything fancy. I simplify the bracket amount first. And let's see, let me move this up some, but now that I'm thinking about it, y'all have already gotten the hang of punching this in. So I can't see what I'm typing there. So here, I punched in the numerator. That's hard to do. I punched in the numerator. I'm now going to divide it by the 0.008. So there's my bracket amount. My bracket amount is 95.21385953. What do I do now to get R by itself? It's R times that number. To undo multiplication, I divide. So I take the 254,400 and divide it by the previous answer. And that's given me an R value. Let's see. Let me move down into the glare score. That's about as good as I can get it right there. Looks like I'm getting an R value of $2,671.88. So these people will have a monthly principal and interest payment of $2,671.88 for 15 years in order to pay off that loan. So let's do another one. Any questions there? Take a moment and look at it. And let's go on to the next one. This is number 2. There it is. It says the following certificate of deposit, CD, was released from a particular bank. Find the compound amount and the amount of interest earned by the following deposit. So this is a CD. What sort of formula are we going to use? We want to find, it looks like it was a $3,000 CD earning 1.16% compounded semi-annually for 3 years. How much, what's the value of that CD after the 3 years? And then they also want to know how much interest was earned. Is this an annuity? Do we have periodic payments taking place? No, no periodic payments. So this is not an annuity. All that's being added to this account is the compound interest. You put in the $3,000 and then every 6 months the bank adds in interest, and at the end of the 3-year period you get your $3,000 plus the interest back. But this is not an annuity. This is just that compound amount formula. Compound amount formula. And A equals P times 1 plus I to the N. So this is number 2. So A equals P times 1 plus I to the N. And let's start going through identifying our unknowns. A, do we know A? No, A is the future amount. That is, we don't know that. We know P. We know the present amount, the principal, the amount of money that was put into that CD was $3,000. I, well, let's say 0.0116, split it up over the 2 semi-annual periods. They're not adding 1.16% interest each 6 months. They're only adding 0.0058. Once again, this terminates nicely. If it didn't, I just use the fraction. And in, how many times are they going to add interest to this account? Well, they're adding interest 2 times a year for 3 years for a total of 6 deposits. So A equals, let me move my paper up now. There, I have all the information I need. A equals, P is 3,000, 1 plus I, 1 plus 0.0058, that's just a 1.0058 to the 6th power. Punching that into our calculator, we get punching that in. What are we getting? We're getting a black screen. Let me see if I can get somewhere. I'm getting a 3105.93. 3105.93. 3105.93. Now what is that? Is that the interest they earned? No, that's just the compound amount. This is the amount of when you cash in that CD, that's how much they're going to give you. But remember, $3,000 of it was your own money. So the amount of interest, what do we have to do? Yes, we have to subtract off the original $3,000 investment. Take that 3105.93 minus the $3,000, that's your own money. Well, you only made $105.93 in interest, but you didn't lose the money. If you put it into stocks, you might have lost it all. So here you have your $3,000. You didn't lose your $3,000, and you got a little over $100 in interest. Any questions there? Notice there were no periodic payments in this problem, so we were not looking at an annuity. So let's come back over here. So on My Math Lab, let's see, My Math Lab, we would have, in the first box right here, the first box, we would have typed in, that would have been the 3105.93. And this would have been the amount of interest, 105.93. Any questions there? And I had one more problem I wanted to do. This one's the biggie. Let's see there. This is like your number 14 in homework aid if you're enrolled in my class this semester. This is like your number 14. A woman with her employer's matching program contributes $700 at the end of each month to her retirement account. So she puts $350. Her employer's putting in $350, which earns 6% interest compounded monthly. When she retires after 40 years of working, she plans to make monthly withdrawals for 25 years. And if her account earns 4% interest compounded monthly when she retires, what is her maximum possible monthly withdrawal without running out of money? So she's saving up. She's going to save for 40 years. She's saving for retirement, and then she's going to start taking out monthly retirement checks, and she wants that money to last her 25 years. That's standard practice for a 401k, a 403b. Once you start receiving your monthly withdrawals, you have 25 years to get the money out. Okay, so that's standard. That 25 years, yeah, that's what it should be. And a word of warning. The wording is a little strange, but the $700, that's the total amount going into her account every month, at the end of each month. She's not putting in $700 and her employer putting in $700. The total amount is $700. She's putting in $350, her employer is matching and putting in $350. So, is this an annuity? Yes, it's an annuity. We're making periodic payments, and well, which formulas are we going to be looking at? Let's see. Hold on. Let me get a sheet of paper here. Lay that down. I'm shuffling the papers around. This is that number 14. There are two big periods. There are two big things occurring on this problem. The first one is the saving process. She's saving for 40 years for retirement. And then after those 40 years, she's going to be spending the money. She's going to be getting the money out of the account for 25 years. So we're looking at a 65-year time span here, okay? This is the number 14. So there are two major things. You have the first 40 years where she's saving. She's saving, what is it, $700 a month. $700 per month. And 6% compounded monthly. That I value would be 0.06 over 12. She's making 0.5% each month. And how many payments is she making into that account? For 40 years, she's making one a month, so that is 12 times 40. She's making 480 payments into the account. And then, once she has retired, she's then going to start receiving monthly payments. She's receiving payments here, retirement payments. She's worked hard, she saved her money, so now she's starting to spend it. And at this point, she's no longer putting new money into the account, and so they're going to drop her interest rate. Her account's only going to be earning 4% at this point. And dividing that by, what, 12? Well, that doesn't go in. That's not a nice, it's that 0.0033. It's a repeating decimal. So I'm not going to use my, I'm not going to use a decimal value. I'm going to leave it as 0.04 over 12. She's going to receive 12 payments for, what was it, 25 years? And 12 times 25, that's 300 retirement checks she's going to get out of her account. And we've already identified I, and I guess that's really all we know right there at this point. So this is for the next, I didn't finish it. Let me see. So this is for year, it's going to be 25 additional years. So there it is, that's year 65. So 0 is when she starts saving. She saves for 40 years. Then for the next 25 years, she's spending the money. Let's deal with the savings. Notice we know more about the savings portion of the problem than the payment receiving portion. All we know here is the interest rate and the number of payments. So let's start with what we know the most of. We know the most about this saving portion. She's making periodic payments, so it's an annuity. Is it going to be a present value or future value? Where does the lump sum occur? The lump sum occurs in the future after those 40 years. So this is a future value of, she's making her contributions at the end of each month. So what sort of an annuity is that? Where you make the contributions at the end of each month? That is a future value of an ordinary annuity. I agree. And we recall the future value of an ordinary annuity formula. S is equal to, okay, I'm moving this up. S is equal to R times 1 plus I to the n minus 1 all over I. And let's identify S. Do we know that? No, we don't know S. That's the future value. How much money will she have saved up in 40 years? So we don't know S. Oops, we don't know S there. But we do know R. She's saving $700 a month. We know I is that 0.005. And we know N. She's going to make 480 payments into her account. So S is equal to 700 times 1 plus 0.005. That's the problem with doing this in pen, isn't it? So that would be a 1.005 to the n power minus 1 all over 0.005. And punching in the bracket amount. Oops, I forgot to silence my phone. Sorry about that. That bracket amount, when you punch it into your calculator, you can't see this amount here, can you? It's 191,490,734, well, whatever that is. Punch that in, then multiply it by 700. So look at the amount of money she's going to have in that account. In 40 years' time, she'll have $1,394,043.51. $1,394,043.51. Well, y'all can't see that. There. So that's the amount of money she has right here. That 1,394,043.51. So she's ready to retire. Now we're looking at the second group, the second time period, that 25 years period where she is making her monthly or receiving her monthly contributions. So we're looking here. Well, looking at this timeline, where's the big lump sum occurring? At the beginning or at the end? By the time she reaches over here, what's her account balance going to be? 0. She's going to spend all the money. So the lump sum occurs at the present. So this is the present value of an annuity. And this is the formula that has the negative exponent. Oh, no, that's just a 1. Minus 1 plus I to the negative n all over I. And I think I'll switch to pencil. I'm making so many mistakes. That's a 1 there, not a parenthesis. So let's identify what we know. P. Do we know P? The present value? Yes, we know that. That's that $1,394,043.51. R, do we know that? No, we don't know that. That's the amount that she's going to receive each month. N, how many retirement checks will she be receiving? Well, let's see. She's getting 12 a month for 25 years. That's a total of 300 retirement checks. And I, we'd already stated that up here, and I'd already said that taking that 4% and splitting it up by 12, it doesn't terminate nicely, so I'm going to just leave it as a 0.04 over 12. So, plugging into our present value of an annuity formula, we're going to get, I'm coming down right here now. Okay, I'm coming down here, so I have plenty of room. I'm going to come right down here. Here's where I'm going to do the substituting in. Okay, I'm going to plug in right there. $1,394,043.51 is equal to R times 1 minus 1 plus I to the negative end, so that'd be a negative 300, all divided by 0.04 over 12. And better dig out our calculators, punch it in. 1 minus 1 plus 0.04 divided by 12 raised to the negative 300. Okay, so at this point I have punched in that numerator. Notice how I enclosed the 1 plus 0.04 over 12 in parentheses. And now I'm going to divide by the 0.0 over 4. So I'll say divided by. And once again, I need to enclose to make sure my calculator does what I want it to do. I want it to perform that division, the 0.04 divided by 12, and then divide the numerator by the denominator. So my bracket amount is a 189.452483. So this bracket amount, I wouldn't write this down if I were you. I'm just doing it here because I want to make a point in a moment. Okay, 189.452483. I'm not clearing off my calculator either. Okay, so it's R times that amount. What do you do to undo that multiplication? Okay, you divide, you take the 1 million, what was it, let me punch it in here, $1,394,043.51. You divide it by the previous answer. Wait a minute. 1,394,043.51 divided by previous answer. Okay, so let's see. Let me move this up right out there. The $1,394,043.51 divided by that 189 point blah blah. It looks to me like the amount of her periodic retirement check, the amount of her monthly retirement check, she's going to be paid well, $73.58.28. I'm getting a 73.58.28. Once we simplified the bracket amount, we divided both sides. We divided the $1,394,043.51 by that bracket amount, giving us a final retirement check amount of. So this is number, let's see, where is that? This was number 14. This was number 14. And so the maximum amount she can receive, what you'd be typing into my math lab, would be $7,358.28. And I think I'll take a break right now, so hopefully this is helping you to see how we put all these financial formulas together. Ask yourself, is it an annuity? Are there periodic payments? And if there are no periodic payments, then you're pretty much stuck with just the compound interest formula, okay? The compound amount formula. Otherwise, if it's an annuity, you have to decide, is it an ordinary annuity or an annuity to you if it's a future value, or is it a present value? Where does the lump sum occur? So I'll leave you to think about that, and I'll go take a break. So bye-bye.